Now we are going to discuss about UV visible spectroscopy. As we in the last class we have discussed about the concept of spectroscopy. Now we are going to discuss about UV visible spectroscopy. What is the region or the wavelength region for UV region and the visible region? So when I talk about the UV region, the wavelength will be ranging from 200 to 400 nanometer. Whereas for the visible region, which is basically the colorimetry region, the wavelength ranges from 400 to 800 nanometer. Right? Colorimeter region, the wavelength ranges from 400 to 800 nanometer. So why we are talking about this UV and visible region? Because in the last class we discussed about X-ray spectroscopy. In X-ray spectroscopy there is a bond breaking and ionization taking place, whereas in UV visible spectroscopy there is an electronic transition taking place. So this electronic transition taking place in the outermost shell, that is in the valency electrons will be involved and having an impact on UV visible spectroscopy. Whereas in X-ray spectroscopy, the bond breaking and ionization taking place in the inner shell electrons. So this is the broad definition or broad differentiation between X-ray spectroscopy and your UV visible spectroscopy. Now when I told in the last class about the UV visible spectroscopy, as I told that the molecule will first go for rotation. Could you see here? The molecule will go for rotation followed by vibration, then going for electronic transition. Now why I am telling these three things? This is in the case of molecule. The original principle for UV visible spectroscopy is electronic transition only. But the molecule cannot jump from ground state to excited state. Further it will undergo rotation. First it will undergo the initial rotation followed by vibration. Then only they will undergo the process of electronic transition. So this is the case of molecule. But in the case of atom, atom is a single entity. In case of atoms, there won't be any rotation, there won't be any vibration. Directly the molecule will move from ground state to excited state by undergoing electronic transition. So what I mean to say, in case of atoms, you will be getting a very sharp line. The band line or the wavelength or the peak will be coming in a very sharp manner because there won't have any interference of rotation and vibration. There you will be getting the pure electronic transition. But in case of molecule, like UV visible spectroscopy, in molecule, you will be definitely having some interference with rotation and vibration, and later on only you can able to measure the electronic transition. Now what is the basic principle of UV visible spectroscopy? In this lecture we will discuss about the electronic transition, the concept of electronic transition. So before going to start about that, whether all the compounds are visible or undergoing this UV visible radiation or not, whether all compounds can absorb UV visible radiation or not, it is not like that. There is some criteria for any molecule to absorb the UV visible radiation. What is that criteria? The compounds which contain the covalently unsaturated groups, that is preferably the pi system, that is nothing but the double bond and the triple bond present in the molecule. Only those molecules will absorb the UV visible radiation. As for example, if you look at the structure of benzene, I will show the structure of benzene. Benzene contains double bond, whereas cyclohexane does not contain any double bond. So what will happen? The benzene can able to absorb the UV visible radiation, whereas cyclohexane will not absorb the UV visible radiation. Why? What is the reason? Cyclohexane does not have this covalently unsaturated groups. This is the main criteria for any molecule to absorb UV visible radiation. Is it clear? Now, when I talk about the electronic transition, basically when we talk about electronic transition, there are basically three types of electrons. One is sigma electrons, another one is pi electron, and the third one is n electron. What is sigma electrons? Sigma electrons are present in the saturated compounds, whereas pi electrons are present in the unsaturated compounds, right? Whereas n electrons are the electrons present in the unshared pair, preferably present in, they are the non-bonded electrons present in oxygen, nitrogen, sulfur and halogens. These heteroatoms you will be having this n number of or n electrons. So these are the three types of electrons involved in the electronic transition in your molecule. One is sigma, another one is pi, another one is n electron, right? Now when we discuss about the principle of electronic transition, so what I mean to say, here I have put sigma, here I put pi electron, here I put n electron, right? So all these electrons are present in the ground state, right? So sigma and pi are the bonding electrons and n is the non-bonded electrons, right? And these are the present in the ground state. But as I told, when the molecule is jumping from ground state to excited state, you should know what is the excited state status also. So in case of excited state, if you look at that, you will be having pi star and sigma star. Okay, excited state means pi star and sigma star. So these are the anti-bonding orbitals. So bonding orbitals are this sigma and pi, which is present in the ground state, whereas antibonding orbitals are pi star and sigma star, right? So if you look at this electronic transition, there are 4 types of electronic transition taking place in any molecule. So I will discuss these electronic transition based upon the concept of energy. So what will happen? The first one is sigma to sigma star transition. You can see here there is a higher energy needed from sigma to sigma star transition, right? And the second important transition taking place is N to sigma star transition, right? The third type of electronic transition is pi to pi star transition, and the fourth type of electronic transition is N to pi star transition. So these are the 4 type of electronic transition taking place in any molecule based upon the energy level criteria. So that is why I have given energy here. Sigma to sigma star transition is greater than N to sigma star transition, which is greater than pi to pi star transition, which is greater than N to pi star transition. So this is how I have made this thing, right? So as far as energy is concerned, which is having the highest electronic transition, sigma to sigma star, and N to pi star is the lowest electronic transition energy, because if you see here sigma to sigma star, it will take more energy. Higher energy is needed for sigma to sigma star transition, and the lowest one is N to pi star. If you look at here, N to pi star, the lowest energy, right? So because this is having a very less energy to cross from N to pi star, this is also called as a forbidden transition or energy less transition. So N to pi star transition is having lesser energy level. The distance from N to pi star is very lesser. So therefore we call them as N to pi star transition, as also called as energy less transition or forbidden transition. Now I will explain some of the examples for this sigma to sigma star transition. Basically sigma is basically saturated compounds and pi is for unsaturated compounds, you know very well, and sigma to sigma star transition mostly taking place in saturated compounds, particularly the saturated hydrocarbons. So what are all the examples of saturated hydrocarbons? Methane, ethane, propane, butane, all these components are having sigma to sigma star transition. So what is this, where you will be getting this sigma to sigma star transition? In the vacuum UV region. That means around 180 nanometer you will be getting this sigma to sigma star transition. Next comes your N to sigma star transition. When I talk about N to sigma star transition, they are present in saturated compound containing heteroatoms. N is nothing but non-bonded, right? So sigma is saturated. So these type of transitions are absorbed in saturated compounds having the heteroatoms. So example is water, methanol. Most of the solvents contain N to sigma star transition. Water, methanol, ethanol, chloroform, carbon tetrachloride, dichloromethane. All these solvents are having N to sigma star transition, right? Because if you look at this transition, these transitions are especially applicable for solvents, and they are particularly here N to sigma star transition. So they are at the end of the UV region. At the end of the UV region originally starts from here, pi to pi star transition. So at the end of the UV region you will be having this N to sigma star transition. So therefore whatever the absorption takes place due to N to sigma star transition in the molecule, so that is defined as end absorption. The process is called end absorption, right? Now the third type of transition is very important, that is pi to pi star transition, because the major concept for your UV visible spectroscopy is concerned with pi to pi star transition as well as N to pi star transition. These are the two important transitions, very important for UV visible spectroscopy. So when I talk about pi to pi star transition, what are all the bands produced by these type of transition? They are present in unsaturated compounds, preferably benzene. Now they have the double bond. If any molecule contains double bond and triple bond, they will undergo definitely pi to pi star transition. So what are all the type of bands produced? Beck bands, that is benzenoid, ethylenic and K for conjugated aromatic compounds bands. Benzenoic rings, then ethylenic bands and conjugated or aromatic compounds. These Beck bands are produced in unsaturated compounds, and these pi to pi star transition, there are different aspects in pi to pi star transition. We are going to discuss one by one. So before we are going to discuss about the concept in pi to pi star transition, we will also know about what is N to pi star transition. N to pi star transition, as I already told you, it is called forbidden transition. The bands produced by N to pi star transition are called R bands. R means the energy is very very less between n to pi star. So R is nothing but resonance. The energy is, when the energy state is very very less, it is called resonance. So the bands is called R bands or resonance bands. And particularly this n to pi star transition are present in unsaturated compounds containing the heteroatom. So what is an unsaturated compound containing the heteroatom? You can have this as an example. Pyridine. Pyridine is basically an unsaturated molecule, that is you will be having the double bond and heteroatom is also present, right? That is your nitrogen. So therefore this is a classical example of n to pi star transition, right? So these are all the various types of electronic transitions involved, and particularly we are going to discuss in detail about this pi to pi star transition. So what do you mean by chromophores? What is the various meaning of chromophores? We are going to discuss this aspect. When we talk about these chromophores, when we talk about these chromophores, what are these chromophores? Right? One is the chromophores. I have told about these chromophores. Chromophores are the covalently unsaturated groups responsible for UV visible absorption. So chromophores are the color producing groups, or these chromophores basically they contains the double bond, triple bond in your molecule, right? So chromophores, if you look at the benzene have the chromophore, right? Benzene, if you look at that, benzene is having 3 double bonds, right? So benzene is a classical example for chromophores, right? So chromophores are having covalently unsaturated groups responsible for UV visible absorption, right? There is another technical term we are giving, that is called auxochromes. What is the meaning of auxochromes? Auxochromes are nothing but these compounds does not have any characteristic absorption of its own, right? I repeat it, auxochromes does not have any characteristic absorption of its own, but when we attach these auxochromes, this is a chromophore, this is a chromophore. Now when I attach the auxochrome here, suppose if I attach the group over here, these auxochromes does not have any characteristic absorption of its own, but these auxochromes, when it is attached on the chromophore, they will either shift the wavelength or the lambda max towards the shorter wavelength region or towards the longer wavelength region. So as I told here, what is this lambda max? Lambda max is basically like this. If you look at here, wavelength versus absorbance. If I plot the graph of wavelength versus absorbance, I will be getting this type of graph. So this is the maximum area. This one is called as lambda max. What is this lambda max? This is the wavelength at which maximum absorbance taken place. Okay, I repeat it. What is called lambda max? Lambda max is nothing but this is the wavelength at which maximum absorbance taken place. So that is called lambda max. And this lambda max is a very very important qualitative parameter for identifying any organic molecule. So how we are classifying depending upon whether it is aspirin, whether it is paracetamol, how will you classify the drug molecule? Every drug molecule is having its unique lambda max value based upon the solvent, right? So this lambda max is a qualitative aspect, identification aspect, and once we are knowing this lambda max, it is very very important what are all the various definitions of auxochromes. So in case of auxochrome, what will happen? Whenever we are attaching the auxochrome, these groups don't have any characteristic absorption. When you attach this group on the chromophore, what will happen? They will either shift the lambda max towards the shorter wavelength region or towards the longer wavelength region. If you look at that, if you shift the lambda max towards the shorter wavelength region, as for example, if I shift the lambda max towards the shorter wavelength region, if you look at here, suppose if this I am shifting towards the longer wavelength region, if I say this is the longer wavelength region, right? If I shift the lambda max, because I am attaching some group here, after the attachment of the group on the chromophore, if I attach the auxochrome on the chromophore, if the lambda max will be shifted towards the longer wavelength region, right? This is the longer wavelength region, then the shift is called as red shift. This is called red shift, which is also called as bathochromic shift. The shift is called red shift or bathochromic shift. Okay, the shift is called red shift or bathochromic shift. Whereas, if I am attaching some group or if I attach some auxochrome on the chromophore, and if the lambda max is shifted towards the lower wavelength region, if it is shifted towards this lower wavelength region, then it is called blue shift, or it is also called hypsochromic shift. Okay, then it is called blue shift or hypsochromic shift. This is the very important difference, you should know that, right? So therefore I have shown here also, you can able to see here very clearly, right? So when there is a shift in, see, chromophores, they have the characteristic absorption of its own, but oxochromes, they don't have any intrinsic absorption of its own. But when I attach the oxochrome group, like for example OH, NH2, OR, any group, if I attach the oxochrome, CH3 group, these are all the example for oxochromes. When I attach this oxochrome on the structure of the chromophore, either there will be a shift in lambda max towards the shorter wavelength region, or there is a shift in lambda max towards the longer wavelength region. If the shift is lambda max towards the higher wavelength region, then the shift is called red shift or bathochromic shift. If there is a shift in lambda max towards the shorter wavelength region, then the shift is called blue shift or hypsochromic shift. In some cases, what will happen? When we are attaching these chromophores with the chromophore, if you are attaching the oxochrome, you will not have this red shift or blue shift. Some cases what will happen? There is only an increase in intensity of the absorption. After attaching the oxochrome, if there is only an increase in intensity of absorption, then it is called hyperchromic shift. Okay, if there is an increase in intensity of absorption, it is called hyperchromic shift, and if there is any decrease in intensity of absorption, it is called hypochromic shift. So this is the basic principle behind this pi to pi star transition. This is very, very important, right? So that is why you should remember that there are different technical terms we are going to discuss, or we have discussed under the pi to pi star transition. One is chromophores, another one is oxochromes, another one is bathochromic shift, another one is hypsochromic shift, another one is hyperchromic shift, another one is hypochromic shift, right? So these are all the very important aspects one should remember in your mind. Thank you very much. Thank you, my dear students.